Hello everyone, welcome to the lecture on 3D computer vision, and today we are going to look at the fundamental and essential matrices, and hopefully by the end of today's lecture you'll be able to describe the epipolar geometry between two views and estimate the fundamental or the essential matrix with 8-point correspondences. And then we'll look at how to decompose the fundamental matrix into the camera matrices of two views and find the rotation and translation between two views from the essential matrix. Finally, we'll look at how to recover the 3D structures with linear triangulation and do stratified reconstruction from uncalibrated reconstruction. Of course, I didn't invent any of today's material. I took most of the content of today's material from the textbook written by Richard Hartley and Andrew Zisserman, Multiview Geometry in Computer Vision, in particular chapter 9, 10, and 11. And I also took some of the materials from the textbook written by Ma Yi and Invitation to 3D Vision, in particular chapter 6. I hope every one of you will take a look at these chapters after today's lecture. So in two-view geometry, we are given two images which we denote as I and I prime respectively. And suppose that we know the image coordinate in the first image, which we denote as X, of a common 3D point that is seen by both I and I prime concurrently. We know from the last two lectures that this particular image coordinate point in the first view, it's going to back project to a light ray. And the 3D point can lie anywhere on this particular light ray. Now let's project this 3D ray onto the second image view. And we can see geometrically that this particular light ray is going to project onto a line on the second image, which we are going to define as the epipolar line and denote it as L prime. So since the 3D point can lie anywhere on this light ray, what this means is that the corresponding point of the first image coordinate can lie anywhere on the epipolar line. We'll further define the epipolar plane, and this plane is simply the plane that is defined by the light ray, the back projected light ray that we have seen earlier on here, as well as another line which joins the two camera centers that we denote as C and C prime here. So we call this line the baseline. And this is simply the line that joins the two camera centers. And we can see geometrically or from this particular diagram here very obviously that the two light rays, the two lines here, the first line which is the back projected light ray as well as the baseline, it spans this particular plane which we call the epipolar plane. We further define the epipole. The epipole is simply the intersection of the baseline with the camera image itself. In two-view geometry, we will have two epipoles, one in the first camera view and the other in the second camera view, which we denote as E and E prime respectively. And equivalently, the epipoles is also the projection of one camera center onto the other view. So for example, in this case, let's denote the two camera center as C and C prime respectively. We see that the epipole, which we denote as E in the first view, is simply the projection of C prime, which is the camera center of the second view, onto the first image. And the relation holds vice versa. So for E prime over here, we can see that it's simply the projection of the first camera center onto the second image. And interestingly, the epipoles are also the vanishing point of the baseline direction with respect to the respective camera center. So for example, in this particular case, in the first view, we can see that E over here, the first epipole over here, is simply the direction of the vanishing point of the baseline. And similarly for E prime over here, we can see that is a vanishing point of the baseline direction with respect to the second camera center. We have seen earlier on what's the definition of epipolar plane. It's simply the plane that is being defined by the back projected light ray as well as the baseline. So this is the plane here. In the example that we have seen earlier on, if we observe a single image correspondence here, this is supposed to correspond to a back projected light ray that is being projected into the second camera view as the epipolar line. And we can see that this relation holds true for any point that we can observe on the image. And every one of this pair of point correspondence, it's going to define a epipolar plane. And hence we'll get one parameter family of the epipolar planes. And interestingly, this particular one family of epipolar planes, it's defined according to the epipose or the baseline over here. The reason is because since there's a unique definition of the camera center C and C prime. So here in two-view geometry, we assume that C and C prime stay fixed. Hence, only one single baseline that cuts across the two respective image planes at the epipole E and E prime respectively. So in this case, E and E are also fixed. And hence, given all the possible point correspondences, we would have a whole family of epipolar planes that must pass through the same baseline. And hence, as a result, this family of epipolar planes must be parameterized by one parameter that revolves around the baseline. We have also looked at the definition of epipolar lines earlier on, and we saw that the epipolar line is simply the projection of the light ray, that is the back projection from the image correspondence of the first view onto the second view. And similarly, for the definition that we have defined earlier on, it's meant for one particular pair of point correspondences, but there can also be many pairs of point correspondences, and each one of these would define a certain light ray that is being projected onto the second view. And hence, we can see that there's also a whole family of epipolar lines on the two views. And what's interesting here is that this whole family of epipolar lines is related to the family of epipolar planes that we have seen earlier on. It's simply a pair of these corresponding epipolar lines, which we denote as L and L prime respectively. It's simply the intersection of an epipolar plane with the two respective camera images. And we also note this family of epipolar line is parameterized by one parameter. The reason is because, as we have said earlier on, that C and C prime, which are the camera centers of the two respective views, stay fixed. As a result, the epipoles E and E prime of the two camera views must stay fixed. And since the whole set of epipolar lines, it must contain the epipole, this means that the family of epipolar line is actually defined by one parameter that revolves around the respective epipole. Now, after we have defined the terminologies of the epipolar geometry, and we have seen that given a point from one view, it actually transfers the epipolar line on the second view. And now we are going to find projective mapping that maps a point from one view to an epipolar line in another view, and define what's called the fundamental matrix as the linear mapping or the projective mapping that maps a point from one view to an epipolar line in the second view. And we'll denote this fundamental matrix as F. We'll first show the existence of the fundamental matrix, and we'll also formalize the exact transfer of the point to a line between two views. So here, the map of a point from one view to a line in the second view, which we call the epipolar line, can be decomposed into two steps. So in the first step, we have two views over here. Given a point in the first view, which we denote as x, we'll define a projective transformation that maps this point onto a point in the second view. In fact, we have seen this mapping or this transfer earlier on, that there's simply a homography that defines this mapping from a point to a point. And then in the second step, after we have defined the transfer of the point in the first view to the point in the second view, which we denote as x prime over here, since we know the epipolar line must contain the epipole, which we denote as E prime over here. And the epipole E prime is simply the projection of the first camera center C onto the second view. So since we know after we transfer x to x prime via a certain homography, we know that the epipolar line must contain E prime, the epipole in the second view, as well as x prime in the second view. We can define the epipolar line L prime. As mentioned earlier on, the first step is that we want to define the transfer of the point from the first view into the second view. And we know in the past lecture that this can be done using 2D homography. Now suppose that we know that the 3D point, which we denote as capital X over here, lies on a 3D plane, which we denote as pi over here. And this knowledge tells us that the image point that we have seen in the first image, which we denote as small x over here, can be transferred to the second image as x prime via the homography, and we can rewrite this particular relation as x prime equals to h pi multiplied by x. We have seen this particular definition in the earlier lectures. Once this is known, we would know that the image correspondence x prime in the second image is related to the first image correspondence as hx. And the next thing that we need to do would be find the definition of the epipole in the second view, which we denote as E prime over here. And as mentioned earlier on, the epipolar line must contain the epipole as well as the transferred point from the first view to the second view. And we can easily define this as L prime equals to the cross product of the epipole and the point that is being transferred from the first image to the second image via the homography. And as a result, we can write L prime equals to a cross product of the epipole and the transferred point. And now let's substitute the transferred point, which is expressed by the homography that we have defined earlier on, into this particular equation over here, and we can easily see that after substituting this, we'll get L prime simply equals to the cross product of the epipole with the homography multiplied by the image coordinate of the first point. Now we can collectively call these two terms over here, the cross product of E prime and the homography, as a single matrix F over here. So note that this particular cross product over here, it's actually written as a skew symmetric matrix. So if we were to take two vectors, A cross with B, we can rewrite this A. So this A here is a 3x1 vector, and B here is also a 3x1 vector. We can rewrite the first 3x1 vector, which is A here, as a skew symmetric 3x3 matrix that is given by this form over here. So I'll leave it to you to verify that this is indeed the multiplication of the skew symmetric matrix of A and the vector of V is equivalent to the cross product of A multiplied by B. So we have seen that this is actually a 3x3 matrix, and the homography, which is the projective transfer, which is responsible for the projective transfer of the point from the first view to the second view, it's also a 3x3 matrix, and as a result, we get the linear mapping of x to the x, which is the image point in the first image, and to the epipolar line in the second view via a linear mapping of a 3x3 matrix, which we call F. This particular 3x3 matrix that we denote as F, we were going to call it the fundamental matrix. And hence, we get the linear mapping relation of a point in the first view gets transferred to a line in the second view via the fundamental matrix, which is a 3x3 matrix. We can see this particular relation, which we have seen earlier on, L prime equals to F of X, as analogous to the homography that we have seen in the first few lectures. So in the case of a homography, we get a pair of 2D image, and there's a corresponding point pairs, which we denote as X and X prime. So in that case that we have seen earlier on, this would be a transfer of a point to a point. And this transfer, we saw that it's equivalent to x prime equals to a homography multiplied by x. So now we have a point and we are going to transfer it to a line, which we denote as x and L prime over here. And we saw that this transfer here, it's going to be related by f, which is multiplied by x, and this is going to give L prime. And the difference here is that in the case of the homography, the transfer must be strictly following a plane in the scene. But in this particular case we are looking at here, the transfer by a fundamental matrix of a point to a line from the first view to the second view. Although it's via two steps, which we define the first step to be a homography, it's important to note that this homography can be on any plane. It's actually a virtual plane that we define in the scene to help us to derive this particular relation of the fundamental matrix that transfer a point to a line. It is not a must that the 3D point lies on a physical in the 3D scene. But in the case of a homography, this strictly must be followed. That means in order for x to be transferred to x prime in two views, actual 3D point must lie on a plane. But in this particular case, it's just a virtual plane that we define over the 3D point to help us derive the fundamental matrix. And furthermore, we can see that since skew symmetric matrix of the second epipole has rank 2, this is obvious from here because we can see that the first two rows, it's defined out of A3 and A2, and as well as A3 and A1. So we can actually take a linear combination of the first two rows to get the third row. Hence, the rank of this skew symmetric matrix must be equals to 2. It cannot be full rank. Hence, the skew symmetric matrix that is defined by the epipole, it must have a rank of 2. And we also saw that in the previous lectures that in order for the linear mapping to be valid, the homography here, h pi, it must have a full rank, which is rank of 3. Hence, the multiplication of a rank 2 matrix with a rank 3 matrix. So this is rank 2 and this is rank 3. The multiplication of these two must give rise to a rank 2 matrix. And that means that the fundamental matrix is of a rank 2. Geometrically, the fundamental matrix actually represents a mapping of a two-dimensional projective plane in the first image to a tensor of epipolar lines in the second image view. And what this simply means is that since we are transferring a point in the first view, which we denote as I, onto a second view, which becomes a line. What this means is that we are actually mapping a projective space of P2, two-dimensional projective space, because it's a point that lies on a plane, and now we are projecting this x to be anywhere, which we denote as x prime over here, on this particular line. Since x prime is constrained to the line, what this means is that now we have a one-dimensional projective space over here. So a fundamental matrix is actually responsible to map a 2D projective space into a 1D projective space. And we have also seen earlier on that the plane that is used to define the transfer h pi, it's actually a virtual plane and is not required for the fundamental matrix to exist. So the fundamental matrix can also be derived in a algebraic derivation. Now let's look at this closely here. So suppose that we have two camera projection matrices that describes the camera pose of the first view, which is cos C, and the second view, which is cos C prime. So this is an image of I and I prime. Suppose that the camera matrices of the two images is given by P and P prime. We know that the image correspondence in the first view is denoted by X. We can derive the back projected rays that is spanned by the camera center as well as X over here in this particular equation that we have seen earlier on. So P plus here is the pseudo inverse multiplied by X. So this defines any point on the light ray and any one point on the on this particular back projected light ray, as well as this particular projected light ray. It must pass through the camera center, which we denote as C. So this light ray can be defined as a span of these 2 points, which means that it's a collection of all the points that is lying on this particular light ray over here. And we parameterize this light ray with a scalar value of lambda over here. Now, let's consider 2 points on this particular light ray. So this light ray is seen from the first camera view, which contains the camera center C as well as the image point. It back projects to this particular line, which we call X of lambda, that is given by P plus, which is a pseudo inverse multiplied by X plus lambda C over here. So let's consider 2 points on this particular line. The first point that we are going to consider would be at lambda equals to 0, and this would be given by the pseudo inverse multiplied by X, and this simply means that it's any point on this particular line. And the second point that we are going to consider would be at the limiting factor of lambda tending towards infinity. And what this means is that we'll get the second point as the camera center, which we denote as C here. So let's now consider these 2 points, and we'll project these 2 points onto the second camera view. And we can see that since the camera projection matrix of the second camera is given by P prime, we can see that the first camera center over here is being projected onto 1 point on the image, which we are going to call it P prime of C. So this point here, we call it P plus of X, is going to be projected onto the second camera, and this results in the projection of P prime P plus of X. So we'll get 2 points over here, which are respectively P prime of X and P prime P plus of X that we have defined earlier on. These are the 2 points that we have seen here. And we know that from the earlier definition of epipolar line is that the epipolar line must contain the reprojected point as well as the epipole. This particular line here is going to form the epipolar line. And the reason why we call this particular point over here, which is given by P prime of C, the epipole, it's simply because the definition of epipole is the projection of the camera center from one view to another view. So this is exactly given by P prime multiplied by C over here. Hence, the epipolar line on the second image can be computed as L prime equals to the epipole in the second image, which is given by P prime multiplied by the camera center of the first image and cross product with the projected point of P plus X onto the second image, which is given by this equation over here, P prime multiplied by P plus multiplied by X. So we have mentioned earlier on that P prime C is the epipole in the second image because it's a projection of the first camera center onto the second image. So this is originally P prime of C multiplied by cross product of P prime, P plus, and X over here. So we can rewrite this guy here into the epipole cross product with this P prime plus and X. And we have seen earlier on that the cross product here can be rewritten into a skew symmetric matrix that is in this particular form. Hence, we'll get this particular equation over here, where we can collectively group this portion here together and call it a F matrix, which is simply our fundamental matrix, and hence we'll get the relation of L prime equals to the fundamental matrix multiplied by the image coordinates in the first image, where the fundamental matrix here, it's given by the cross product of the epipole multiplied by P prime and P plus. We can check the correctness of this fundamental matrix. It's supposed to be a 3x3 matrix over here, and we can see that the cross product, the skew symmetric matrix, that is defined by the epipole. It's also a 3 by 3 matrix, and we can see that P prime over here, it's supposed to be a 3 by 4 matrix, and P plus, since it's the pseudo inverse, this is supposed to be a 4 by 3 matrix. And if we multiply these three matrices together, we'll end up with a 3 by 3 matrix. And this form of the fundamental matrix that we derive algebraically, we can see that it's similar to the fundamental matrix that we have derived earlier on using the geometric derivation. So where the homography simply is given by P prime multiplied by P inverse. And here we can also see that from this definition here, from this particular outcome of the derivation algebraically, we can see that the homograph that we defined earlier on in order to help us to transfer a point from one image x here to transfer it to the second image x prime over here is simply a virtual homography. This means that the particular 3D point, which call capital X, it need not necessarily lies on a real plane for this homography to exist, because this homography is simply a function of the camera matrices of the two views P and P prime over here. A remark over the algebraic derivation of the fundamental matrix is that this derivation that we have seen earlier on, it breaks down when the two camera centers are the same. What this means is that it degenerates, and we cannot make use of this algebraic derivation to derive the fundamental matrix when the two camera centers are the same. So the proof is here. If we have seen earlier on that the epipole on the second view, so here's two views, I and I prime. The epipole, which we define as E prime in the second view, is simply equals to the camera center of the first view being projected into the second view, which is P prime and C. So in this particular case, where C simply equals to C prime, this means that the two camera centers are the same. We can see that the projection of C into the second view, which is P prime multiplied by C, is going to be a null matrix over here, which is 0 over here. And this follows that if we were to plug it into the equation that we have derived earlier on for a fundamental matrix, since the skew symmetric matrix here is defined based on E prime, which is equals to P prime multiplied by C over here. And in this case where C equals to C prime, this guy over here simply equals to 0, and the whole equation here will simply vanish and becomes 0. This proves that the algebraic derivation breaks down when the two camera centers are the same. We'll look at one example over the algebraic derivation of the fundamental matrix. Suppose that we have two camera matrices of a calibrated stereo rig. A calibrated stereo rig simply means that we place two cameras on a fixed rig. That means that the two cameras is rigidly attached to a rigid body over here. And calibrated simply means that we know the intrinsic value of the first camera K and the intrinsic value of the second camera, which we denote as K prime over here. And so we by this form of definition, we can assign the camera matrix of the first view to be a canonical camera matrix, which is given by K multiplied by I and 0. So this is actually a 3 by 4 identity matrix. This simply means that the camera coordinate aligns with the world coordinate over here. And the second view here is simply rotated and translated by R and T over here. And hence, the second camera matrix can be expressed as the intrinsic K prime multiplied by the rotation and translation of the second view defined with respect to the first camera world frame. Then we can easily find the pseudo inverse of the first camera matrix over here, which is defined by this guy over here. So pseudo inverse, as we have seen earlier on here, is simply given by the 3 by 4 matrix of P multiplied by P plus equals to identity. We can solve this. P multiplied by P plus equals to identity, and since we know this guy here, we can plug it into this, and we can solve for P pseudo inverse over here, and as a result, we'll see that this is equivalent to K inverse and 0 transpose over here. So this is actually a 4 by 3 matrix. And C, which is the camera center, since we define the first camera projection matrix to be in a canonical form, what it simply means is that the camera center of the first camera is going to be 0, since the world frame is aligned with the camera coordinate frame. And by plugging P and P prime into the equation of the fundamental matrix that we have seen earlier on here, we can simplify this equation, and finally we'll see that the fundamental matrix is actually an expression that is given by the camera intrinsics, which is K prime over here, as well as the camera extrinsics, which is R and T over here between the two views. So we can further make use of the two camera matrices that we have seen earlier on here, P and P prime, to define the epipoles in the two views respectively. So now we have two images, I and I prime over here. We know that the camera matrix of the first view is given by P equals to K multiplied by I and 0, as well as P prime is equals to K prime multiplied by R and T, which can be rewritten into K prime multiplied by R and minus R C, which is the camera center over here. What this simply means is that from this relation, we can tell that minus R C tilde is equals to T, and this implies that the camera center can also be rewritten into minus R transpose of T over here. So we know that the epipole of the first camera view is denoted by E, and this epipole over here, which we denote by E, is simply equals to the projection of the second camera center, which is C prime over here, into the first view. So this would be simply equals to P multiplied by C tilde that we have seen earlier on, and 1. And this is equals to P multiplied by minus R of transpose of T and 1 over here, which is exactly what we see here. If we were to plug the first camera matrix in terms of the intrinsics and the extrinsics value into this equation over here, we can simply express the epipole of the first camera view as K multiplied by R transpose of T. We can do similar things for the epipole that we denote as E prime in the second image, since E prime is simply equals to P prime multiplied by the camera center C of the first image. Since the world frame and the camera coordinate frame are aligned in the first camera, we can simply write this as P prime equals to 0 and 1 over here. And plugging in this particular expression of P prime into E prime, we can see that we'll get this particular relation over here, which is K prime multiplied by T. And what this means is that if we were to look at this expression, which consists of this guy over here, Kr transpose of T, which is equivalent to the first epipole, we can rewrite this part here as the first epipole multiplied by whatever expressions that we have earlier on. As well as we can see that K prime of T, which is the second epipole here, it appears also in this particular equation here. So we can also rewrite this term here into E prime, the cross product of the epipole with K prime R multiplied by K in, and this is the relation here. Now, so far, we have looked at transfer between a point from one view into another view. We saw that this transfer is actually a point, which we denote by small x over here in the first camera image, and we transfer it to a line in the second image, and vice versa. So this line is actually the epipolar line, which is L. And we saw that this transfer is via the fundamental matrix. So the fundamental matrix essentially maps X into a line, L prime over here. And now suppose that we know that these 2 points, X and X prime, are corresponding points in two views. If we know x in one view, we know that x prime must lie on any point on the epipolar line in the second view. But now, suppose that we start from the point correspondences. That means that given two images, which we observe x in one of the image and its corresponding point x prime in the second image. We know these two are correspondence. X and x prime are correspondences. So we ask the question of whether there's any relation simply these two correspondences, and it turns out that the answer is yes. We can actually derive a correspondence condition, which is simply given by this famous equation in 3D computer vision over here. So x prime transpose f multiplied by x must always be equals to 0 as long as x and x prime are correspondence point in the two images. So the proof is very simple because we know that x prime must lie on the epipolar line in the second view, L prime, which is given by f over here, which is here. So we can see that x in the first image is transferred to the second image as an epipolar line. We know that this epipolar line must contain the point correspondence of x, which we denote as x prime. So what this simply means is that there must be an incidence relation between x prime and L prime. And what this simply means is that the dot product of x prime and L prime, which is the epipolar line, must always be equals to 0. And since we know that L prime is given by the fundamental matrix multiplied by the first image coordinate point, which is f multiplied by x, substituting this relation into L prime over here, we get the famous equation of x prime transpose f multiplied by x equals to 0. There's a very important significance of this particular equation, x prime transpose f multiplied by x equals to 0. This simply means that we can actually compute f, the fundamental matrix over here, the fundamental matrix over here, simply from the observation of point correspondences between two views. This is analogous to what we have seen in the homography case. We saw in the homography case that given 4-point correspondences, if we know that these 4-point are correspondences, we can simply compute the homography, the 3x3 homography that relates these two views, that transfer this onto a set of corresponding point in the second view. The fundamental matrix, unlike the homography, it's going to transfer a point from the first view onto an epipolar line that contains the corresponding point in the second view. And this is a significant importance of this particular equation over here, which means that we can compute the fundamental matrix directly from the point correspondences without any knowledge of the 3D scene nor the 3D geometry of the camera poses. We'll discuss later on how many point correspondences are needed to compute the fundamental matrix from this particular correspondence equation over here. Now, let's look at some properties of the fundamental matrix. We saw that the fundamental matrix, it can be expressed in terms of the two camera matrices P and P prime in this particular order. And what's interesting is that if we swap the order of P and P prime, this simply means that just now we define the first image to be I and the second image as I prime over here, which means that the camera matrix of the first image must be P and the second image must be P prime over here. Our derivation is based on this ordering. So we'll get we saw earlier on that we get the expression for the fundamental matrix, which is F is simply equals to P multiplied by C, and this cross product multiplied by P prime and P pseudo inverse over here. That this is the relation. So this particular fundamental matrix over here is defined based on the ordering that P is the first camera view and P prime is the second camera view. So suppose that we are swapping the order right now. That means that the first image over here we call it I prime and P prime. The second image over here we call it P and I. Then F transpose would be the corresponding fundamental matrix over here. We can see this very clearly from the correspondence equation. So we saw that X prime transpose F, X equals to 0 over here. So this relation will also hold if we take X prime transpose F, X, and transpose the whole thing. So this would become X transpose F transpose and X prime equals to 0, where we can see that this is simply a swap of the order. Previously, the first point here belongs to the second image, which is X prime. And the second point here is the image correspondence in the first image, which is denoted as X. So once we do this transpose, we can see that the first point here, which corresponds to the second image, becomes X. And the image correspondence that corresponds to the first image becomes X prime, and hence the corresponding fundamental matrix becomes F transpose, as we have claimed earlier on. Here's some property of the epipolar line. For a point in the first image, the corresponding epipolar line is L prime equals to Fx. So if we were to look at the other way around, L equals to F transpose of X prime simply represents the epipolar line of the corresponding image. What this simply means is that we have two views. If we were to look at the first view I and I prime over here, the first view with a point X over here is going to get transferred to the second view as L prime, and this is going to be equals to F of X. But if we have a point here that we denote as X prime, this point over here is going to get transferred over to the second view here as L prime, and L prime is going to be equal to F transpose of X prime over here. So again, we can simply see the relation over here in this particular equation over here. So in the first equation over here, X prime F X defines the incidence relation between the point on the second image and the epipolar line. So this is the epipolar line L prime over here on the second view. So this is an incidence relation, and this must be equals to 0. And the second equation over here, which is simply the transpose of the first equation, it also defines the same incidence relation, but in the first view. So we can see that now X transpose here is the point in the first view, and F transpose X prime defines the epipolar line in the first view, and that is since the point on the first image must lie on the epipolar line in the first image as well. The incidence relation over here, the dot product of these two, of the point and the epipolar line, would simply be equals to 0, and hence fulfilling this equation that we have seen earlier on. And now let's also look at some properties of the epipole. So for any point X other than the epipole in the first image, the epipolar line must contain the epipole. We have seen this earlier on, that this particular epipolar line that is being transferred from a point X in the first view via F over here. So this guy here is L prime equals to F of X. It must contain the epipole over here, which is E prime. This simply means that because there's an incidence relation between the epipole and the epipolar line L prime over here, so this simply means that the dot product of the epipole with the epipolar line must always be equals to 0. We can also rewrite this particular equation. So this is the incidence relation, which is E prime transpose of L prime. This simply means that the dot product of the epipole in the second view and the epipolar line in the second view must always be equals to 0. Can be rewritten into E prime transpose multiplied by F and X. Since we know F multiplied by X equals to the epipolar line in the second view, and this must also be equals to 0. And we know that X here is not going to be 0 for it to be a valid image point. So since this equation can be rewritten into E prime transpose of F multiplied by X, and we know that X here is never going to be 0, what this means is that the multiplication of E prime transpose and F must be equals to 0 in order for this relation here to hold. Hence, we can rewrite this equation into a null space equation of E transpose F equals to 0. What this means is that E prime is simply the left null space of F. And similarly, we can also derive this equation over here, which means that the epipole in the first image is simply the right null space of the fundamental matrix F. We can also see that the fundamental matrix has 7 degrees of freedom. Fundamental matrix F over here is a 3 by 3 matrix with 9 elements in there, and we have to minus away 2 degrees of freedom. One, because there are only 8 independent ratios. The scale here is not important, and the second thing here is that because we have seen earlier on that the fundamental matrix is of rank 2. This means that the determinant of the fundamental matrix must be equals to 0, and this reduce 1 more degree of freedom. Hence, as a result, we have 9 minus 2 equals to 7 degrees of freedom for the fundamental matrix. And another property of the fundamental matrix is that it's not a proper correlation. So what this means is that it's not invertible. We saw that the relation of a fundamental matrix is actually a linear mapping function that maps a point x onto the epipolar line in the second view. So L prime is equals to F multiplied by X over here. And the determinant of F equals to 0, and it's not full rank. Although it's a 3 by 3 square matrix over here, the relation is only one directional. What it means is that the inverse of F simply doesn't exist. And here's a table to summarize the properties of the fundamental matrix that we have seen earlier on. So it has 7 degrees of freedom, and the correspondence equation is given by F prime transpose F of X, and then the epipolar line in the two views is given by F X and F transpose X multiplied by X prime. And we also seen that the epipoles are given by the left and right null space. And we also seen the algebraic derivations that the fundamental matrix can be expressed as the epipole and the camera projection matrices that we have seen earlier on. And here there's a significance of this. What it simply means is that if the two camera matrices P and P prime are uniquely defined, that means that we know this uniquely. What this means is that the fundamental matrix would also be unique. So this means that given a pair of P and P prime matrices of the camera, we will only end up to have one particular unique fundamental matrix that defines the mapping of a point to a epipolar line between the two views.